Okay, so today we're going to be learning about exponential functions. I'll go ahead and fill that in the blank right here. And exponential functions are actually one of my favorite topics to teach just because they have so many applications to what's going on in today's world. Some would even say that the coronavirus is modeling an exponential function, which can be argued. But it has other applications such as loans and investments and savings accounts. There's so many different things that can be modeled by exponential functions. So it's actually a really cool topic for me to teach. Now, the thing about exponential functions, it's not like linear functions. Linear functions, which we've learned about at the beginning of the semester, linear functions look like this, and they grow at a constant rate. Exponential functions, in contrast, they are growing by something called a growth factor, or maybe even a decay factor, which we'll get into in just a bit. But before I do that, the general form of an exponential function can be modeled by f of x, which is the same thing as y, equals c times a to the x power. Now there's two parts here. This c value, sometimes it's a c. You can also use other letters. I've seen some people use the letter b. But that c is our initial or principal value. That's what we're starting the function out with. Right here, initial value. And then the other part of this exponential function is this a term. Now this a term represents something called the growth factor. It could also be called the decay factor, so I'll go ahead and put growth or decay factor, depending on if it's growing, getting larger, or lessening, decaying. So there's two parts, and if you know those two pieces of information, you can create an exponential function. Now let's go ahead and start with what an exponential functions table looks like. So for this first example, we're given a function, and let's say the function wants to double with every 1 unit increase in the independent value variable x. So basically every increase by 1 in x, we're going to double the output f of x, or y value. So I've already given us a starting value, 0 and 5. So if we increase the x value by 1, so from 0 to 1, the y value, the output, will double. So instead of 5, the double amount of 5 would be 10. Alright, as we increase one more in the x value, so one more would be 2, the y value would now double again. Now when I say double again, I mean the last value would double. So 10 would double, which would be 20. And then lastly, as we increase the x value one more to 3, the last y value, which was 20, doubles again, which was 40. So if you're looking at this, you can see each y value is doubling. It's being multiplied by 2. It's getting pretty large pretty fast. Okay? And that's pretty much what a table would look like. Exponential functions don't have to double. They can also triple or quadruple, or they can multiply by 100. They can also lessen. They can also half or be multiplied by 1/4, and etc., which we'll look at more examples. Alright, now what we're going to do first is we're going to figure out how to identify what type of functions are linear or exponential. So remember, linear is just constant functions. They increase by the same amount each time. So for example, if I had the y value of, 2, and it added 2 each time, so my next y value would be 4, my next y value would be 6. It's adding 2 each time. That's called just a constant function, adding the same amount each time, or subtracting the same amount each time. So what we're going to do is we're given 3 tables here, and I want us to identify which ones are linear, which ones are exponential, or maybe neither. Okay, so let's go ahead and start with the first one. If we look at all of the x values, they're all increasing by 1, -1, 0, 1, 2, and 3. So it's just adding 1 each time. And if you look at the y values, I'm going to go ahead and start with 5. And it subtracts 2, because subtracts 3. 5 minus 3 is 2. So let's go ahead and see if it subtracts 3 again. 2 minus 3, is it -1? That is correct. Each time it's subtracting 3. It's adding or subtracting a constant number. So it's subtracting 3, subtracting 3, subtracting 3. Nothing is changing. The same amount is being subtracted each time. And when that happens, that's a constant function, also known as a linear function. So our first table is called a linear function. Okay. Alright, so if we look at our second table, if you look at the x values are increasing by 1 each time. And the y values, well, it went from 32 to 16. Now, one could say it subtracted 16 and you would be correct. But if you look at the next two rows, 16 minus 16 would not be 8. 8 minus 16 would not be 4. So it's not subtracting by 16 each time. That's not the pattern here. However, 32 and 16 are also related in a different way. It's being halved. Half of 32 is 16. So I could also say that 32 is being multiplied by 1/2. Same thing for the next two rows. 16 is being multiplied by 1/2 to get 8. And 8 is being multiplied by 1/2 to get 4, and so forth. So if you look at the pattern, it has a constant or the same multiplier each time is being multiplied by 1/2. When that happens, that's called an exponential function. So our second table would be labeled as such. Okay. So linear functions have a constant add or subtract number that's being either constantly added or constantly subtracted from one to the next. And exponential functions have a number that's being multiplied constantly from one to the next. All right, and then our last table, if you look at the x values, it's increasing by 1 again. But if you look at the y values, first, let's see if there's an addition or subtraction constant value. From 2 to 4 is being added 2. But 4 plus 2 is not 7. So we know that there's not a constant number that's being added to them. So I can cross out linear. I know it's not linear. So I put not linear. All right, let's see if there's a constant multiplier. 2, well, if I multiply 2 times 2, that'll give me 4. But if I try to do the same thing with the next two rows, 4 times 2 is not 7. So that won't work either. So there's not a constant multiplier either. So this would be not exponential function. It might be another type of function, we're not sure, but all it's asking us is to look at is if it's linear, exponential, or neither. And in this case, it's neither. So that's how we could identify linear or exponential functions, just by looking at a table of values. All right, this up here on top is pretty useful. I gave us the original form, f of x equals c times a to the x power. It's the same thing. There's some people use different letters. This person used c, this textbook used a and b's, but it's the same thing. They all represent the same thing. There's two parts to it. The first part is a, or the number in the front, the coefficient, and that's just your starting amount, your starting or initial value. What are you starting the function with when x is 0? So starting amount. And then the b value is your growth factor. How much is it growing by? What's your multiplier amount? Just like on this previous example, see how it was multiplied by 1/2 each time? That would be our b value, 1/2. So that's what it's being multiplied by each time. It can also be called a decay factor, depending on if it's larger or smaller than 1. So there's two parts to it, which I said earlier, and then x is just our variable that we're going to be using. Now, it can be called, an exponential function can be called either a growth function, an exponential growth function, and I've also heard it called increasing function. I think that's the word they use on your homework, so I'll go ahead and write that down. And you know that if a function is going to be increasing, meaning the y values will get larger and larger and larger, if the growth factor, meaning the b value, is greater than 1. So if this b value is a number that's bigger than 1, you know it's going to be increasing, meaning it's going to get larger and larger and larger y values. If the growth factor or / decay factor, if the b value is between 0 and 1, meaning if it's a fraction basically between 0 and 1, or a decimal, then it's going to be called an exponential decay function. I've also heard decreasing, and I think that might be on your homework, so I'll go ahead and use that terminology as well. Okay, but that's how you can tell, is the exponential function going to increase or decrease over time. If we look at the previous example, the second table, if you look at the y values, they're getting smaller and smaller and smaller. It's because the growth or decay factor was less than 1, greater than 0, between 0 and 1, which is 1/2. It's basically a fraction. That's how I knew it was a decay function. So an easy way to tell if your function is going to grow or decay over time. Okay. All right, so now that we've covered the basics of the equation of exponentials, next thing we're going to do is we're going to learn how to graph these types of functions. So we're going to go ahead and start with example number 2. Example number 2 says graph the exponential function f of x equals 2 to the x power. So let's go ahead and I'm going to take this and I'm going to go ahead and start with figuring out what is my a and b value. I'm going to go ahead and write it out larger out here to the side. Well, I know that 2, because that's the base of the exponent x. That's the number that's directly attached to this exponent x. 2 would be our, according to this formula, that's our growth factor. And it's greater than 1, so I know it's going to grow. So I'm going to go ahead and just label it. That's our growth factor. That's what it's growing by each time. That's the multiplier. Now, there is technically no a value written. There's no coefficient in the front of this. But if you want to add a coefficient, you can always add one without changing the value of anything. And that number is 1. So technically, I could put a 1 here. That's not changing the value because anything times 1 is itself. I just want to have a specific a value written so I know that that number is going to be my starting amount. Okay. Now you have two options. You could make a table for this if you wanted to. You can go ahead and create a little mini table and plot some points. I'll do a few if you want to do it this way, and then I'll show you another way that I do. So when your x value is, let's go ahead and start with just, let's go ahead and start with 0. What would the y value be? Well, we can plug in 0 for x, so this will be 2 to the 0 power, which anything to the 0 power is 1. So I can go ahead and plot the point 0, 1 on my table. I would just create this table by making some more points. When my x value is 1, the y value, or the output value, would be 2 to the first power, which is just 2. So I have 1, 2, I can plot that point as well. When my x value is 2, the y value will be 2 to the second power, which is 4. And you get the gist. You can go ahead and create as many points as you want. Now what I kind of do, you can use a table, and that's a very safe way to plot some points. You can also go ahead and just look at your graph and start with the starting amount, which is 1. That's what the y value will be when x is 0. So when x is 0, the starting amount will be 1. So I know that I can go ahead and plot the point 0, 1, and you'll see that that's also a point on your table. And as every increase in x goes by 1, the y value increases by 2. It doubles. So x is 0. When x is 1, my y value was 1, but what's double 1? Well, it's 2, so I can go ahead and make it 2. Or you could just plot the points that we had in the table. As my x value increases by 1, so my x value is now 2, the last previous y value will double. So it was 2, it'll now be 4. And so on and so on. It might be helpful to actually get some negative x values so you can kind of figure out what's going to happen over here. So if you wanted to make a negative x value, let's say negative 1, the y value would be 2 to the negative 1, which, if you're not sure what that is, you can use a calculator to help you, but it's actually just going to be 1/2 or 0.5. So negative 1.5, right somewhere around right here. Back 1, up half a spot. And once you have enough sufficient points, you can go ahead and connect them with a solid line. And there's our graph. So it kind of looks like a flat line, and then it kind of just curves up. And that's generally the shape of most exponential functions, or growth functions. They kind of have a flat line, they kind of curve up in some way, because it's increasing over time. Okay. All right, next one, example number 3. Same thing, it just wants us to graph this exponential function. This one, though, I notice is going to be a decay function because the growth factor is smaller than 1. It's between 0 and 1. I'm going to go ahead and start the same way. I'm going to go ahead and figure out what is my growth factor and what's my starting amount. I'm going to write it larger out here to the side. We have 1/2 to the x power. Now I know 1/2 is our, I say growth factor just out of habit, but it's called a decay factor because it's smaller than 1. Okay. And that's how much it's going to be multiplied by each time, the y values. Now there is no a value in the front, there's no coefficient, but you can always write one without changing the value. You can always put 1 times this, and it won't change the value of anything because 1 times anything is itself. And that's our initial or starting amount. So you can go ahead and use the graph if you want to go ahead and just kind of base it off of starting amount and decay factor. You can also make a table of values. If you want to plot some points, that's also fine. I'll go ahead and just create a few points and I'll plot them. So when x is 0, our y value will be 1/2 raised to the 0 power. So I'm just using this equation, which is just 1. So I can go ahead and plot that point 0, 1. When our x value is 1, our y value will be 1/2 to the first power, which is just 1/2 or 0.5. So I can go ahead and plot that point 1, 1/2, which is over 1, about half up. When x is 2, our y value is 1/2 to the second power, which is 1/4 or 0.25. It's getting smaller and smaller. So I'm going to try my best to plot that last point. Over 2 units, up 1/4 units, which is kind of somewhere right there. I'm going to go ahead and get some negative x values to kind of help me fill in this part of the graph. When x is -1, our y value will be 1/2 to the -1 power, which is actually 2. So I can go ahead and plot that point, -1, and then up 2 spots. And you can create a couple more points, but I think that's good enough. I'm going to go ahead and just connect those points with a solid line. And there's our graph. All right, up here at the top of these notes, I went ahead and created some properties of just exponential functions that kind of apply to just all exponential functions. The first one being that the domain is the same for all exponential functions, and that's that the domain will always be -infinity to infinity, or all real numbers. Just pretty much means that for all exponential functions, you can use any x value. There will never be any undefined or error values that you can plug in and get that. So domain is the same for all exponential functions. The range is actually the set of positive real numbers from 0 to infinity. So that's pretty nice. It's always the same for all of the exponential functions. There are no x-intercepts. If you look at the previous 2 graphs we just did, there wasn't any x-intercepts. The graph kind of curved out, it flanned out. It never actually crossed the x-axis. It got really close to it, but it never actually intercepted the x-axis on either of those. And that happens because there's not going to be any x-intercepts. It never actually crosses the x-axis. Okay. And then the y-intercept is 1. Well, for this case, for these 2 cases especially, the y-intercept was 1. Okay. And the x-axis is a horizontal asymptote, which you've kind of seen. It never crossed the x-axis. It kind of just got really close to it. It's called that means that the x-axis is a horizontal asymptote. Okay, so just some nice little features about it, in case you want to refer to those that are always true about exponential functions. Okay. All right, we're going to go ahead and do one more graphing using transformations, and then we'll go ahead and move on to the last part, which is solving. So example number 4, it gives me another exponential function, and it says to graph it and also determine the domain and range and horizontal asymptote. Now, the thing about this function, it has a little extra part to it. It has a -3 on the end that we're not used to seeing, but it kind of relates similar to what we did when we learned transformations. So first thing I'm going to go ahead and do is I'm going to go ahead and I'm going to create a table to help me plot some points. So I'll go ahead and start with just the most basic one. When x is 0, our y value will be, well, I'll plug in 0 for x, it's going to be 2 to the -0 power minus 3. And you can do the math on that, but 2 to the 0 power is just 1. 1 minus 3 is a -2. So I can go ahead and plot my first point, which is 0, -2. Okay. When x is 1, my y value will be 2 to the negative 1 power minus 3, which is 0.5 minus 3, which is negative 2.5. I'm going to go ahead and try my best to plot that. 1 comma negative 2.5 is somewhere down here. When x is 2, my y value will be 2 to the negative 2 power minus 3, which is negative 2.75, which once I plot that, that looks like 2 comma negative 2.75 somewhere down here. I kind of see that it's flattening out. I'm going to go ahead and get some negative x values to kind of fill in this part of the graph. When x is negative 1, the y value will be 2 to the negative 1, because a negative was part of the formula, and then x itself is a negative number, minus 3, which is just 2 to the positive 1, minus 3, which is just negative 1. So negative 1, I can plot that point as well. And then we'll do one more point. When x is negative 2, the y value will be 2 to the negative 2 minus 3, which is just 2 to the positive 2, which is 4, minus 3 is 1. So negative 2 comma 1, and that's right here. I'm going to go ahead and connect these, and there's our graph. Now this graph's a little different because that minus 3 kind of changed it a little bit. Now the thing that differs here is this graph is very similar to the graph of 2 to the negative x, but this minus 3, all that minus 3 does, if you remember what we did with transformations, it just takes the graph and it shifts it 3 units down. That's what this minus 3 does. And I think there might be a few questions on your homework that ask you, what does the minus 3 make the graph of 2 to the negative x do? And it makes the graph shift down, because remember, anytime you subtract a number from the end of a function, it shifts the graph down. Okay. So as far as my domain and range, well, domain, remember the domain is the same for all exponential functions. It's just all real numbers, or you can also write negative infinity to positive infinity. Just means it goes all the way back and all the way forward. And then our range, now our range, well, the general one was 0 to infinity, but that's with no transformations. So if you look at the range, that's just the lowest the graph goes, and the lowest the graph goes, it kind of levels out at this negative 3y value. So our range would be from negative 3, and there's no maximum amount. The graph kind of continues on in the upwards direction forever, so it would go up until infinity. Okay. And then lastly, it says to list the horizontal asymptote. Now in the general guidelines up above, the horizontal asymptote was the x-axis. However, this graph was shifted 3 units down, and so the horizontal asymptote is now this horizontal line, which is the line y equals negative 3. So these guidelines apply to basic exponential functions that don't have any transformations. If you do have transformations like we did here, a minus 3, then it's going to change some of this information a little bit. It's going to skew it. But for the most part, we can use these guidelines to kind of base off our answers from. Alright, I'll go ahead and leave that next one for you guys to do if you want to do practice, but it's the same thing. You can plot some points and make a sketch of the graph. Alright, the last part of this lesson is how to solve exponential functions. So we're going to go ahead and start with example number 6. So example number 6a, it's given us an equation. Now x is in the equation, and we're supposed to solve for x somehow. Now we could try to sit here and try to plug in numbers and think, what x value can I plug in to make this whole equation true? That might take a while. So if you look at this equation a little closer, one of the left-hand side has a base of 3. The right-hand side, it doesn't even have an exponent. It's the number 81. But if I recall my powers, and I think of the number 81, well, I do know something about 81. I know that 3 to the first power is 3. I know that 3 squared is 3 times 3, which is 9. I know that 3 cubed is 3 times 3 times 3, which is 27. I know that 3 to the 4th power is 81. 3 times 3 times 3 times 3. So looking back at my equation, instead of writing 81, I'm going to rewrite it as 3 to the 4th power. I'm not changing the value of it, I'm just writing it a different way. So instead of writing equals 81, I'm going to write equals 3 to the 4th power, because 3 to the 4th is 81. Now the reason why I did this is because if you look at the equation now, the bases are the same. 3 to the x plus 1 power equals 3 to the 4th power. The bases are the same, so essentially you know that the powers will be the same. You can think of it as just crossing out the bases, or you can just think of it as, oh, the exponents must be equal. So what I now know is that x plus 1 is going to equal 4, because the powers must equal each other. And that's an equation I can easily solve. What number plus 1 is going to equal 4? Well, subtract 1 from both sides, and x equals 4 minus 1, which is 3. And there's our x value. Now, how could we check that this answer was right? I mean, we were pretty careful, but how could we, if we wanted to check that 3 was the correct answer? Well, we could plug it in to our original problem and see if it gives us a true statement. So let's go ahead and do that. We have 3 to the x, which we said x is 3, so let's go ahead and plug it in, plus 1, and we want to see if it equals 81, which you can go ahead and test out right here if you just want to type it in. And what do you know? It equals 81. So that's a nice way to check pretty much all exponential equations when you solve them. All right, and then part B. We have another exponential equation. This one does have a base of 4 on the left-hand side and a base of 8 on the right-hand side. Now, on the previous problem, I knew that 81 could be rewritten as a base of 3 to the 4th power. If you look at part B, though, 4 and 8, they don't really have the ability to be rewritten as a base of the other. 8 cannot be rewritten as 4 to the something power, because 4 to the first is 4 to the second is 16. See how I can't really write 18 or 16 as 8. So we can't use a base of 4. But if you think about 4 and 8, they have another factor in common. They both have a factor of 2. So let's look at our powers of 2. Let's see, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 2 times 2 times 2, which is 8. And you can keep going, but I can kind of stop here because I already see how I can rewrite both of these bases. Now, 4, instead of writing 4 to the 2x minus 1 power, I'm going to rewrite 4 as 2 squared. So on my left-hand side, instead of writing 4, I'm going to write it as 2 squared. Now, we still have this power, this 2x minus 1 power, and so I'm going to go ahead and just write that on the outside. So we have like a power with another power, and that's okay. And on the right-hand side, instead of writing a base of 8, I'm going to rewrite it as 2 to the third power. And we still have this power of x plus 3 on the outside, so I'm going to go ahead and rewrite that as well. Okay. Now the cool thing that we've done here is we now have the same base on each side. That is the goal. You want to have the same base on each side. Because if you have the same base on each side, essentially, you can pretty much just cancel them out like we did on the previous problem. So this base of 2, I'm just going to cancel out with the other base of 2, because I know that if the bases are equal, that must mean that the powers are the same. So once I cross out these bases, all that I'm left with is I am now left with a power of 2. And then I still have this 2x minus 1. And then on the right-hand side, I have this power of 3. And I also have this x plus 3 that's in the exponents section as well. And now we're left with just a linear function or linear equation that we can easily solve by distributing and solving for x. So let's go ahead and do that. We'll start with multiplying 2 times 2x is 4x. 2 times negative 1 is negative 2. On the right-hand side, we have 3 times x is 3x. And 3 times 3 is 9. we've distributed. Now our next goal would be to combine all of the x's by getting all the x's to the same side. It doesn't matter which x you want to move over. I always like to move the smaller one over, but it doesn't matter. So I'm going to move over 3x, and the way we move it to the other side, it's a positive 3x, so I'm going to subtract 3x once on each side of the equation. And what I'm left with is 4x minus 3x. Well, 4 minus 3 is 1, so it's just 1x, or you can leave the 1 off, minus 2, equals 3x minus 3x, those canceled out, and we just have 9. And then last step, what number minus 2 is going to give us 9? We'll just add 2 to both sides, and x is going to equal 9 plus 2, which is 11. And again, you could always check that this was right by just going back and plugging in your answer to the original problem, and it should give you a true statement if you did it right. Right. Okay, and then last part is really just calculator practice. These are all exponential expressions. They're called exponential because they have exponents or powers on them. And all this is a matter of is just making sure that you know how to evaluate them properly on the calculator. I don't expect you to try to evaluate this by hand. That might be a little tricky. 2 raised to the 1.4 power, you would just type in the 2. And in order to get that 1.4 in the exponent section, you just use this little caret symbol. And then you type in 1.4. And it's 6.390 dot dot dot. I didn't say how many decimals to round to, but we'll go ahead and round to 4 decimal places. So this is approximately, and since I'm rounding, I use these approximate symbols. 2.6390. It's 0.1, so it doesn't round up. So it's just 0. Same thing for the next problem. I would just type that in. I would type it in as 5 using the caret hat symbol. And then 3.6 minus 1, that entire thing is in the exponent section. And I get 65.6631. So I'm going to put this is approximately 65.663, and it's 19, so the 1's going to round up to a 2 if I'm rounding the 4th decimal. Next one, negative 2 to the 4th. Negative 2 raised to the 4th power is negative 16, and I didn't even have to round on that one, so I can just put equals 16 since I didn't round. And this last one, it says the letter E. Now some of you might have heard of E. E is actually a pretty famous number that not a lot of people know about. It's a popular or famous irrational number. Most people have heard of the letter pi, 3.14. Most people don't know of E, which is just as popular and I think should be given just as much recognition. But it has a lot to do, it's a naturally occurring number that has become famous, mostly because it occurs a lot with loans and investments, and savings accounts, and just all exponential functions. And that number is about 2.71. You can go ahead and type it in. If you might have a different calculator, but I know mine. If you look at this little ln symbol, it's the letter E in small blue letters. So I would push the second button and then the LN button. Most calculators should be in the same location. And if you notice, it'll pop up the letter E. And if you just want to figure out what is E, it's about 2.71 and has some more decimals. But it goes on forever, just like pi. It's an irrational number that continues on forever. But the problem just wants us to figure out what is e to the negative 1.3. So I'm going to type in e to the negative 1.3, and that's approximately 2.2725. And the fifth number is a 3, so it doesn't round up. And that's it. Alright, if you have any questions, you can email me, but hopefully that should give you a good start on your exponential functions chapter homework on my math lab.